right, so in this part, so again, this is part of one of the trainings in REMARO, and I think later on in the next training, I think Adal will be continuing a little bit more on optimal control and linear quadratic regulators. That's hopefully in the next training in Delft, if I'm not mistaken. Then I'm going to be talking about a use case of docking. So you saw the videos a bit in the morning. I'm going to talk about how we're really doing it. And then Christian is going to talk again for another use case, which is the control of the Cuttlefish robot. All right, so without further ado, we can start. So now you'll be a bit surprised, like, why am I talking about this very simple thing, a mass damper spring? And the reason, if you have a look a bit on the equations of a mass damper spring, it's basically just the mass by the acceleration. Then there is a friction term, and there is the constant of the spring here. So assuming that x is the motion or is the position of this mass or of the center of the mass, and my control is some control u. Now, if you take a closer look on this very simple equation, what does it look like? It looks very similar to the dynamics that we saw on the first session. So here's inertia, could be inertia plus added inertia. Here is damping, and here is restoring forces. So basically, by just providing controller for this very simple system, we can then just extrapolate it to more dimensions and then talk about control of a rigid body free floating in the water. So let me just transform this form into this second order differential equation. I mean, it is a second order differential equation. If I just divide by the mass, and then we could write it as the following. So x double dot plus this 2, this zeta, and omega n by x dot plus omega n squared. And we will call these two terms, omega n is the natural frequency of this system. So it's the frequency that it will, if I give it an impulse, and which is basically just like I take a hammer and then I hit it with an impulse of like 1, it will like oscillate with this frequency. And this damping ratio basically is like how much the amplitude of this oscillation will decay. All right. So if we, for example, this is what I'm just talking about. If I take an impulse, let's assume that this period is 1, or this frequency is 1, so that's like 2 pi. I mean, then we can design it. We can choose the mass and the constant of the spring accordingly. And then basically here, what I'm trying to do is just to play around a little bit with the relative damping ratio. So if I choose it 0, this means that there's no damper at all. If you just kick the system, it will just oscillate forever with this frequency of 2 pi basically, or this period of 2 pi. And when you start increasing this damping ratio a little bit, you can see how this signal is kind of getting dampened or getting a little bit trimmed down till in the end converges to like 0 if I put lots of damping in the system. Now, very similar effect if I use a step response. So a step response is that I push the system to, let's say, a magnitude of 1, and then I just keep it there basically, or I keep this force or acceleration or whatever I'm using to kick the system. And you can see also very similar behavior. So if the damping is 0, it will just oscillate. If I increase the damping, it will oscillate and then decay after a while. And if I put a lot of damping, it will not oscillate at all. It will just like directly go and then achieve this step response that I'm taking. Now, this is when we're talking about the system in a time domain. Now we can also talk about frequency domain. So frequency domain is basically if we take any function in the time domain and then we do a Laplace transform on it using this formula, we can try to we can transform basically this function to this S, or basically then it's a complex plane. So if we have a system G, assuming that this system is a linear system, and if we give it as input some wave, let's say a sine omega t, if this is a linear system, the output or the response of the system basically will be of this form. So basically, it will vary the amplitude of this signal, and it will cause a phase shift. So this phase shift, we can see it here as phi. And basically, this is kind of useful to study the stability of a system. So we can see which frequencies I can control the system with, and which frequencies then the system starts to become unstable, or where are the frequencies that the system is completely dampened. So we can basically, by taking this function g of I omega, if we get the magnitude of it, we're going to call it A, so that's the amplitude, and if we get the phase of it, or the angle, is basically phi in this case. So by doing this Laplace transform to the time domain equations, we can transform it into the S plane, or the frequency domain. So that's going to be, for any function, basically the Laplace transform is going to be, let's say we have x of t, it's going to be x of s, by basically just taking this equation here. And then if we take the time derivative of, let's say x, so x dot, the Laplace transform will be s multiplied by x of s, and double derivative s squared, and so on. And then basically, to get this transfer function g of s, the only thing that we have to do is just divide y of s by u of s. And then we will get this kind of transfer function, which we know called as a second order transfer function. Now, the way we can think about this transfer function, we can just, as I said, we can just try to excite the system with different frequencies and then plot these amplitude and phase shift. And this is what we call here a Bode plot. So you can see here, this is the frequency on the x-axis, and then here's the magnitude, and here's the phase. So what does that mean? This means, like, with very low frequencies, the magnitude that I'm gonna have is very close to the magnitude of the input. However, if I have very high frequencies, then there is a huge decrease in the magnitude. But at a certain point, you can see that there is a little bit a rise. And this basically, we call that the resonant frequency of a certain system. Now, to demonstrate it, actually, I can do that. Maybe give me a second. So I'm not sure. Can you see me? So I just unplugged this very crude mass damper spring system, which is just the phone. I hope our IT department doesn't cause some trouble. Let me just stop sharing the screen for a second. And so basically, this is, as I said, I hope you can see it on the camera quite well. So that's a kind of a mass damper spring system, right? So if I excite it with very low frequencies, let me get a little bit further away. If I excite it with very low frequencies, you can see that the amplitude of this mass that I have here is kind of the same as the amplitude of my hand, which is like the excitation that I'm giving it, right? This is basically the left part of this Bode plot of the amplitude. However, if I take my hand and then I shake it quite fast, so that's a very high frequency, you can see that this is just shaking in place, right? It's not going up and down. And that's why we see like this kind of slope going down with the amplitude. Now, there is a kind of sweet spot, or breaking spot, more like it, somewhere in the middle. If I actuate it with a certain frequency, look how small I'm moving my hand. I mean, of course, this is now shaking in this plane as well, but you can see that this is kind of oscillating a lot. And that's what we call the resonant frequency of the system. So if I take you back to this slide, so you can see this frequency, basically you can observe it here, which is like the thing that we usually want to avoid because it will cause our system to break. Basically, if we are just giving in a small input and then what we're getting as output is like a very high amplitude output. However, we also notice if we look at the phase, basically at some point, the phase when I started, it was the same So whenever I start moving down, the mass part was also moving down and up with me. And if you go like for a very high frequency, you would notice at some point that there will be a phase shift of 180, which is kind of the same. However, at this point, and like where the resonance of the system, or where the magnitude is kind of getting very high with respect to what I'm giving it as input, you will see also a phase shift of around 90 degrees. So when I'm moving my hand up, the mass is all the way down, and when I'm moving my hand down, basically the mass is all the way up. And that's basically what we want to try now to manipulate these kind of resonant frequencies by basically just changing the characteristics of the system. So the way I would choose this natural frequency of the system and the damping would basically control for me where is this resonant frequency. So the more I push this to the right, this means that this frequency only occurs at a higher, or this resonance basically, or this very high amplitude occurs at a higher frequency. The more I'm kind of giving gain to my system, so-called. And the more I give damping, the more I'm gonna try to slow down this, or to get rid of this peak. And this is basically, you can see it if you just like simulate that system and then just play around a little bit with damping. So just solving this differential equation and doing this this boat plot. So here you can see like the blue kind of represents very low damping in the system. So you can see how the peak is really high. And when I start adding damping, you can see how this peak is kind of getting tamed, reaching here to like a nice and smooth curve basically. So we are not, so no matter how fast or how slow we are kind of shaking the system, it is not causing like a very exaggerated response, let's say. And here's also how you can see how the phase kind of is a little bit changing. So now if we vary the natural frequency of the system, so you can see basically we just push this resonance, or this resonant frequency, a little bit forward. However, we decrease also a little bit the magnitude with it. So we can see here, like the more we take it forward, the more kind of we are giving ourselves more room to play around with. So in this part, like more frequencies, I can make use of more frequencies to control my system. All right, so that's just the basic thing of this spring and damper. However, I mean, in reality, we have one system. So we identify our system. We have an AUV, for example. It has some dynamics. It has a mass. It has a shape. It has that kind of determines our damping. And what we want to try to do is we want to find a way to manipulate this natural frequency and this damping. And this is how we're going to see. So the simplest thing we can do is to add a so-called KP controller, PD controller. So a PD controller is basically just a proportional and a derivative. So I close the loop. This is my system here, and this is my controller here. So I close the loop. I take my state and I feed it back, and this is my reference R. And then every time I'm just calculating the error between my reference and between my state. So in a time domain, KP basically, this input U is just a proportional gain. So I'm just multiplying this error by a certain gain. And I'm also calculating the time derivative of this error. Now, if RT is fixed, then this is basically just the time derivative of X. And I'm multiplying this also by a certain gain. Now, if I transform it to the frequency domain, then U of S would be, since this is just derivative, becomes S. So KP stays the same, KD multiplied by S, and then here is RS minus XS. However, here we add also a little bit of damping to the system. Disturbance, not damping. D is for disturbance. So also with my control, we have, I don't know, current or some kind of force that is pulling me away from where I want to go. Now, a small recall. So this is how my system looks like now. So this is the differential equation that describes my dynamics. This is my control, which is I just determined here. And this is the disturbance. Now the disturbance, I still don't know what it is. I have to model it in a way to be able to deal with it. However, there is also a way to eliminate it. Now, if I just plug this equation here and then I rearrange a little bit, I'm basically just dividing by this polynomial, and taking all the stuff that is a factor of s. So I'm factoring s out and then just dividing by this omega s. So what I arrive at is basically this Kp plus Kds multiplied by the reference that I want to try to achieve minus the disturbance, all divided by this polynomial, or we call this the characteristic polynomial s. Now by doing this, you can see that I just changed my system, or this polynomial basically. Since this Kd is multiplied by s, I changed basically, I can now control how much damping in the system there is. I can also control what is the natural frequency of the system can become by manipulating those terms, because this is something I can choose freely. All right. Now, if I calculate the error again, so basically just Rs minus Xs, I can just rearrange this equation a little bit and then become something like this. So let's consider just a step reference. So a step reference, the transfer function for it will be R over S. So a step reference is like everything below 0 is 0, and then at t equals 0, I jump to a reference R. So just taking a step function and then multiplying it by R, and also just a step disturbance. So also a constant disturbance. So whenever I start actuating my system, there is a disturbance. There is something called the final limit theorem, which is basically means as t tends to infinity, or as s tends to 0, this error basically in the end converges to only this term here, which is basically just d over kp plus omega n squared. You can do the math if you like. I mean, I'm just giving you the final result. So what can you see here? This means if I choose kp to be very large, I can get rid of this disturbance in there, right? So this kind of, as this tends to be a very large number, this tends to be, the whole thing tends to be a low number, which is the error that I'm trying to get rid of, because this disturbance now is also causing me more error that I don't want. So again, taking this characteristic equation, just recalling it from the last slide. So here I can write the new system, let's say, as the following. So basically now this new system that I have, or this new characteristic polynomial, is kind of s squared plus 2. I call this zeta c, which is the controlled omega c plus omega c squared. So omega c squared is just the square root of this term, and then you can calculate that term zeta c basically is just 2, the old relative damping and the natural frequency, plus kd over 2 omega c. Right, and this way basically, so I can choose whatever natural frequency or new frequency of the system and a new damping ratio, and then based on that, I can use these equations here to calculate what is the necessary gains, so the proportional and the derivative gain that I need to control this system. And here's an example. So we just saw that before, right? So if I choose, let's say, the natural frequency or the new controlled frequency of the system to be 1, this basically would determine for me the value of kp. And then if I vary a little bit these guys, so here I have a damping of 0, so this is just oscillating, so this is not what I want. And if I increase the damping a little bit, so if I add a little bit more of derivative gain, I will reach to a smooth system that is converging to the command that I want to have. Here's basically a step command of 1. All right, so let's now, sorry, we are still here without disturbance here. Sorry, here's the value if I just vary the natural frequency. So here I was just varying fixing the frequency and varying the damping. And here I'm fixing the damping and I'm varying the frequency. So in blue here is the low frequency of the system, which is is low gain. And the more I push it forward, the more I increase this value, the more my system is more responsive. The faster I reach the step reference that I want to have. So basically by increasing this means I'm increasing the gain or the proportional gain as well. And this is how you can observe that. Now, if you increase this a lot, this means you are driving the system to be a little bit unstable again, right? So here's like how you can design your system by playing around with your frequency of the system and the damping or the relative damping ratio of the system. So here, if I would add a disturbance, let's say a constant disturbance of just 0.2. Now, only having this 0.5, so now starting here, this disturbance basically will push my system. So I'm not achieving it anymore here, right? So here, this 0.5 was actually performing quite well. So after a couple of seconds, it was reaching the step response that I commanded it. However, now if I introduce disturbance to my system, look what happens to that. And then if I try to increase more and more the gain here, or this kind of controlled natural frequency, the more I get closer to the value that I actually desire. However, you can see here that there is always a little bit of error. There's also some fallbacks to having very hard or very high values of omega C. This basically means that your controller is very stiff. And this means that you are, let's say, your command or your actuation is kind of a thruster, which is what we're talking about. This means that you are pushing your thrusters really hard to be able to achieve the control that you want, which is not a very good thing to do. I mean, you are basically reducing the life of your hardware, or you are causing the system to like reach some kind of an unstable response. Now, how do we do to get rid of this? So naturally, we want to try to use a moderate gain or a moderate, so for example, something like 1. However, we cannot get rid of this error somehow because we have a certain disturbance. And here's where we can introduce the so-called integral term. So this integral term, we just also take the error and we integrate it. And basically by doing so, like the transfer function of that is just ki multiplied, of course, by some gain ki. So it's just ki over s, right? So now if I have a look at my system, I just redo again this stuff. I have kind of a third order polynomial, which includes here the I in it. So if I would do also the first of all, like let's see how what this thing does. So here's a ki of 0, and if I increase, so here my damping ratio is 1 and the frequency is also 1, which was before this yellow plot here, right? So we had an error. And here now, if I just add a bit of integral value, so basically I'm taking all these errors all along when I start here all the way up to here, I'm taking these errors. So of course, when these errors kind of decrease, so integrating basically means just adding zeros, which doesn't have so much effect here. It's having most of the effect in this region until we reach a certain. So basically just by adding a bit of integral gain, we can get rid of this so-called steady state error. Okay, so here's kind of as a summary, like what can happen. So this is, let's say, the same system. So if I only start with a P controller, so just a proportional controller, if the P is too low, then I do not reach the reference that I try to achieve. If my P is very high, this means I'm giving more natural frequency to the system. I will start to oscillate at some point. If I increase a little bit but introduce damping to my system, I will get rid of these oscillations but at some point, because of disturbances, would get a steady state error. And if I add an integral action, I will get rid of this steady state error and then achieve this nice and smooth red curve here. So looking at it a little bit in the frequency domain. So this is basically what we're doing or how we are manipulating our system. So our system here was this blue curve. Maybe it's a little bit hard to see here. So our system was originally this blue curve. Now, if I add only a proportional controller, what I'm doing is basically what I explained before. We push this frequency a little bit forward. So we have a little bit more wiggle room to play around with. If we add a derivative part, we are adding more damping to the system. So this switches to the green curve here. And then this green curve, basically, you can see that it was following the yellow one here. However, we got rid of this peak. So this kind of unstable behavior, we removed it a little bit. And then adding the I in the end will basically introduce into my system lower frequencies only, which help me get rid of this steady state error. All right, so why we are talking about this, all of it, just as a small introduction to take all of that knowledge and now apply it into the control of an underwater vehicle. So any questions here before I move to this second part? Okay. Then let's move on forward. So just let us recall a little bit the equations of motion that we have here. So the kinematics, and this is the dynamics, and we are going to assume here, I mean, we did a little bit of simplification, so we just lumped the mass and the added mass together. We assume that at the moment there is no ocean currents, so there's only one V, or we can estimate it somehow and then take it into account, but just for the sake of simplicity. And we assume that we can observe the position. So let's call this here the position. Let's give it this big eta, which is basically just the putting both position and attitude or orientation in the same vector. And V is putting the linear angular velocities. So if I have an observer that can measure for me those states, I can design a PID controller of the following form. So the tau that I'm going to choose it is basically taking the error of the pose, multiplying it by a proportional gain, by a derivative gain, and by an integral gain. And then the only thing I have to do is just to transform it to the body frame, because this arrow is actually still in the inertial frame. So this is position, and this is the orientation, either Euler angle or quaternion arrow. So basically this tilde eta is the reference minus the measured position. And if I take this control signal, put it in the body frame, which gives me the wrenches in the body frame, then I could use any control allocation if my system allows it. So I can use control allocation that Christian just talked about earlier to control my robot. This is the simplest kind of that you can think about. However, the way that you want to tune these, so basically KP here is a matrix, of diagonal elements, right? So for each degree of freedom, we have a different gain. And then you could have a look at your system. If you have those values, if you have identified your system, you can take a look at them, and then you can see how do you want to tune those KD and KP and KI to kind of achieve a stable response of the system. So as I said, this is just a very simple controller here. Now, what we are basically trying to do here, however, is we are trying somehow to control a linear system, a nonlinear system with a linear controller. So PID here is just a linear controller, right? But what we talked about here, this D part was causing for us a little bit of problems before. So if I can model it a little bit better, I can try to make use a little bit of the model a bit more. And this is what I'm going to talk about next, which is what we call model-based control. So let's now take a look again in our system, and then we just lump all of these parts here. So all of the forces, we just lump them into one vector n, which let's say represents all the nonlinear forces and moments that are being experienced by the body. And this is, of course, a function of the velocity states, and you can put phi, you can put the quaternion, you can put the rotation, whatever you prefer. And let us, I mean, if we don't have, let's say if we know the perfect model here, right? If we know that, and this is, let's say we have a simulation, and then from the simulation we can know perfectly what is m, what is n, because we designed them. Now, if we have a reference orientation and reference velocity and acceleration, sorry, and the reference orientation, the simplest thing we could do is we just give this, we just calculate it, and then from this we can calculate the actual torque that we need to move our system to these values that we have. This is simply what we call open loop control. However, this has the drawbacks that we don't take into account any disturbances. So if we add disturbances here, then these two, they don't equate anymore. And if our n or m is not the same as here, then we will also get an error. So the simplest thing to do is to just add a PID controller on top of that. So what we are doing here, we are just helping our control to first go to a value which is very close to what I think my system is. So like I have, let's say, I don't know, some kind of reference, some trajectory generator that is giving me at every instant what is the orientation position that my robot should have, what is the velocity, and what is even the acceleration, depending on what kind of trajectory generator or path planner you have. So if I have instantaneous values of all of these states, basically, I can use the model to try to get to an actuation, or try to get to a force and torque values based on this model that are what I think is the closest to my system, and then everything else I can correct with this PID controller. This is what we can find the system called, if you read about it in literature, it's called feed-forward control. So feed-forward means we take the model that we have, we take the reference state that we want, we feed it to the model, we calculate the torque that we have, which is this feed-forward torque, and then we have a PID. I mean, this could also be any kind of other controller, so it's not necessarily a PID controller. So this is how kind of the flow would look like. So we have our reference, we feed it into the model, we feed it into the controller, and then from the AUV we have a state observer that will give me the states. Here, for example, this could be a Kalman filter or whatever. It gives me the states, and then I can calculate the error here. So here I'm closing the loop. However, if I take this part out, we don't have a closed loop. We just have an open loop, just the feed-forward alone. If I close the loop between those, I kind of make it easier to my controller to kind of provide as least amount of correction as possible. So instead of just going from 0 without anything, so taking this arrow from 0 all the way to the point that I want to reach, and using the controller to do that, I give it first an initial guess by whatever torque I need, and then I let my controller correct the rest. So this simply is what we call feed-forward control. Any questions so far? Okay. So another kind of trick that we can use to control our system is what we call feedback linearization. So this time, instead of feeding in to the model the desired states, I'm going to try to use the model to linearize my system, therefore making it also a little bit, making my life easier to tune my PID controller. So if I have a linear system, it's way easier. So what I will do here, so this again, our equations of motion, we're going to choose a control law, which basically is the following. So the control law basically is the mass or the inertia of the system, if I know it, multiplied by, let's call it an acceleration AB. It's an acceleration command in the body frame, plus, if I can observe those values, of course, I just take this part of the model, all the nonlinear parts, and whatever the state observer is giving me, I can also feed it into this nonlinear part. And the only thing that I have to control would be this signal here, as if I'm giving as input the acceleration of the system in the body frame. Now, if you take this and plug it back here, these guys will cancel out if I have an accurate system. They will not completely cancel out because there are always uncertainties in the model, but at least I will try to get rid as much as possible of all of this nonlinear behavior. And then in the end, well, the mass matrix, if you just multiply by the transpose of it from the left, then you also get rid of the mass matrix. And this is basically what we get in the end. So the system dynamics is basically, this is what we try to control, the acceleration of the system, by basically just giving an acceleration command. So we're just controlling a linear system plus some disturbances that we also try to reduce a little bit by kind of inverting the mass matrix. So like we are dividing by the mass, kind of, which reduces also the disturbances a little bit, or the effect of that. And let's go ahead and choose this control signal, or the acceleration control signal. So if we differentiate, first of all, the kinematics with respect to time, so we want to calculate the acceleration in the inertial frame, so which is this eta double dot, is basically just the chain rule. So the transformation, or this J multiplied by V dot plus the derivative of J itself multiplied by V. This means that this V dot basically is just the inverse of this transformation multiplied by the acceleration in the inertial frame minus the velocity, or this derivative of the, or the Jacobian basically of this transformation multiplied by the velocity. And so this is, if I now substitute that, so this AB, since this is acceleration and this is acceleration, so this is AB in the body frame, and this is AI in the inertial frame. I can also write it the same way. And now if I just come and take AI as a PID control, for example, simply just taking the same. So I have the arrow and the position, or the pose, I have the derivative of the arrow and the integral of the arrow. Then I can just plug this back in here, and then I can control the acceleration in the body frame. Take this guy, plug it back here, and then I'm basically controlling a system only based on the acceleration. So I'm giving directly a command to the acceleration. And then if we draw it here, so this is my system here, this is my reference and this is my state observer. Now the difference is that the feedback linearization, so I take from the state observer the pose and the velocities, I feed it back to my model. Of course, you can transform this using this equation here to V. So if you just multiply by the inverse of J, and then you have in the body frame the velocities, you can also, or the state observer maybe gives you directly the velocities in the body frame. You add it on top of that, and then you take those to the PID controller. You transform this acceleration command into the body frame multiplied by the mass matrix, and then just add it into the system. And this way we kind of cancel out non-linearities, or we linearize the system, and that's why this is called feedback linearization control. All right, now, I mean, these are just basic control architectures that I'm just going to talk about for now. Later on, I think Kristen will also mention a little bit what is a cascaded PID control. So that's also this very simple concept, just a PID control put on top of each other. And also later on in one of the research lectures, let's say, also Kristen will talk about model predictive control and the work he's doing on that. And in the next training, Erdal will talk a bit more in details on optimal control and linear quadratic regulators. Other control algorithms that you might also find in literature, like there's backstepping control, sliding mode, fuzzy logic. There are lots of different controllers, but these are the most basic control algorithms that you would find for underwater robots. Now, the next thing I'm going to talk about is docking and how we use one of these controllers that I just talked about now for controlling the AUV that we have to do docking. So any questions before on the theoretical part, before moving on? I think now it's going to be less equations and going to be more results and more videos. And I see a hand, Carlos, yes?
Hi, Bilal. Thank you very much for an impressive overview of control techniques. I'm curious which controllers are more used in which different underwater robots, because at the beginning today you mentioned different types of robots, and I'm curious on a daily basis, and maybe it's a question that you can answer, but maybe there is also other people here that have direct experience of, oh, we are all the time tuning this controller or this, and I'm curious about that, which are the most common.
Exactly. So currently on most of our robots, the ones that let's say we know that they work or that we are using the most are this one here, so the feedback linearization. So we have a PID controller that we have to tune not that much because we can identify the model of the system and then feed it back, and the cascaded PID controller. So I think Kristen will talk about it briefly later. So the idea of cascaded control is just so that we have a PID controller of each of the motion states. So for the position, there is one controller, for the velocities, there's one controller, and for accelerations. And the idea is just you want to cancel out disturbances at the source. So if your disturbance is in the form of currents, if it's velocity, for example, you can try to cancel these out with the velocity controller. If your disturbance is more a force applied on the body from some other source, then you can cancel that on the acceleration level. So these two are the ones that we know that they work. The ones that we are still experimenting with is LQR and MPCs. And I'm going to mention also a bit later, there is one PhD student also on another Marie Curie project, a colleague of ours who trying to apply so-called LQR trees. So he kind of divides and conquer the problem into different linear system where he knows that LQR works. So you can optimally find a solution for each of those, and then it's kind of like a funnel that fits into another funnel. So you can guarantee with certain conditions, of course, the optimality of this control law. So this is still experimental. Like we want to try it next on one of our vehicles. We did it mostly in simulation so far. All right. Any other questions? Sasan, yeah?
Do we have any guarantee for the robustness or the stability of the system for any of the approaches?
So far, no. This is, of course, we go into the idea of robust control. So that is something we should do. We are not doing at the moment, but of course, I mean, the way that we are tuning the controllers is basically what I just mentioned before. So we try to identify the system. We assume that, not to assume, based on how much error we get between the measured data and the output of the system, how good, or we kind of can evaluate how good this model is. And then based on that, we try to select controllers that has kind of, so the way that we do it is that we try to shape this frequency plot and infer the gains from that. But real robust control group that is working here at the institute that is working more on that topic. But on the vehicles themselves, no, not yet.
Okay, thanks.
Yes.
I also have a question. Do you use any learning-based control strategies as well, or?
Yes, this is also, yeah. So also a bit spoiling for the next session. So, I mean, the way, of course, since we do as well, in the beginning, the talk of Frank was most about AI, but learning-based. So there are two ways. The way that, or the thing that I'm going to talk about later in the afternoon is how to learn the model instead of doing system identification to have a more accurate representation of the dynamics, option A, and then use this either in a model predictive control or for canceling out nonlinearities or whatsoever. And the other way is reinforcement learning. So this is also a topic that I mean, I want to keep some of the stuff for other for other events in REMARO. So I was thinking of doing a talk about it for this workshop, but I decided not to because of time constraints. So just keeping things a little bit more under the same. But yeah, so there is a student that is doing his master's thesis with me at the moment on using reinforcement learning to do docking with an underactuated underwater vehicle. And the goal is to see how much these compare to other or classical control methods that we're just discussing now.
Maybe a follow-up question in sampling-based methods, like A-star sampling-based methods, like A-star or like a graph graph-based.
Yeah, so I mean, this is sampling-based methods are more for path planning, right? So here, these methods would give you your reference. So would give you any of these methods, right? So if you have a map of your system or a certain domain, or you can discretize the system, this is more a path planning method. So yeah, I'm not doing the actual control, but so if you're asking us like how we do the path planning, at the moment is we use our rapidly random exploring trees, so RT methods so we have some kind of a component that will give you a map of based on acoustics, based on cameras, will give you like well, not a 3D point cloud, but an occupancy grid, like a 3D, like an octomap or octree representation, and then give that to a path planner that uses RT with a certain time to find a solution, and the propagation function in the RRT method or RRT star is being the kinematic equations of motion. So at least we guarantee that the path that this RRT is giving us can be traced by the vehicle.
Okay, yep, thanks.
Okay, any other questions? All right, so let me then move on to docking. So exactly, so I'm going to talk about like one of the things, let's say, that we do the most here, or which is like also distributed over several projects and over several AUVs. I think you saw a couple of videos in the morning. And the scenarios, of course, also Professor Kishner talked about them. So why do we need docking? To be able to have the vehicles or subsea resident AUVs. If we want to have a vehicle for a longer time underwater, that it comes back to this kind of cocoon or cabin of it, and then recharge batteries, download new missions, and upload whatever data it collected. And the scenarios here is also like can take that into space exploration or extraterrestrial ocean exploration, which is also part of one of the projects that we work on here. So we also have a docking station that after exploration, the robot can come back and dock into this station and then transfer information. So the approach that we do that is basically a little bit inspired by aviation. Actually, the website more than paper. It's the way that airplanes land on a runway basically is kind of, they evaluate this based on this precision approach path indicator. So there are some parameters, like for example the approach angle and the distance, and then you can see here then they assume, okay, if the vehicle is above this inclination angle, then it is too high, or the distance that you have there, or if it's below it, then it's too low. So there is like some indicators, and then if you're on a right glide path, then you have to decide, okay, to abort or to adjust a landing of an airplane. And what we did basically, we took kind of the same idea here, and then we tried with our docking station that you just saw. So this is like this docking station is part of the Europa Explorer, was designed in the Europa Explorer. You can see it's like a very narrow docking station, which makes it quite harder also for us to dock. Other research groups doing docking, you can see that there are lots of these docking stations that they have quite a big opening. Also, even if the robot hits somewhere, it can it's like a funnel that would force the robot mechanically, let's say, to dock. However, because of space constraints here, we cannot do that huge opening angle. So the docking station is really just fits the robot exactly. Now with Flatfish, of course, it's a little bit bigger, but kind of the same concept. So the vehicle itself is also a little bit bigger. So this is what we exactly do here. So we define kind of a range that you can see. The green part here is where the robot is on a right glide path or on a right slope to reach the docking path. And when it gets to the red parts, then it's not so good. And if it's above, if it exceeds those paths, so basically we just abort docking and then just go back and try again. I'm gonna show a little bit later also the state machine, how we do that. So the same thing vertically. So just take this and put it vertically. So if you're also approaching from the sides. And to talk about docking, one of the hardest part actually is not the actual control itself, but more the state estimation. So to do that, we have this following approach. So docking is kind of based on three behaviors. So first of all is homing. So that's when your vehicle is away from the docking station. You cannot see the docking station visually. And the things that we rely on here is acoustics. So by using a sensor called ultra-short baseline, or USBL. Maybe some of you are familiar, some of you not. The idea is just triangulation in the end. So there's a pinger on board of the vehicle, and then the USBL sensor is basically an array of hydrophones placed next to each other in a very close range. But by measuring the phase shift, so imagine here you have an emitter and sending an acoustic signal, so the only thing that you can measure is the time of flight, and then you can get the range, right? By having three of them, if you calculate the phase shift between the different times that each receiver gets the signal, you can estimate also not only the range, but also the azimuth and the elevation angle. So with this kind of sensor, if we are very far away from the vehicle and if our observer has drifted quite a bit, we can try to rely on such communication method or positioning method to find our way back. Now, once we get closer and we can see visual markers, this is the next part. This is when docking starts. And docking itself is composed of two different behaviors. So first of all is aligning. So that's when we see the marker, and then we try to get in this green zone that I just showed in the slide earlier, and align our heading also with the docking station. And then once we are on this glide path towards the docking, then we start, let's say, the docking approach. And this is mostly done based on visual landmarks like Aruku markers. You can see here a lot of them on the docking station. However, these are not the only sensors that are used here. So to talk a bit more about this observer that we have, so I'm not gonna go so much into the details of what is an unsent Kalman filter, but it's an observer. It's like a model-aided inertial localization based on an unscented Kalman filter. And the sensors that we have, or the whole sensor suite that we have on the vehicle, is what I just mentioned earlier. So there's a camera with marker detection for close range, and there is a USBL for long range or for the homing. Then the basic dead reckoning is basically a pressure sensor that would give you a depth IMU, or here in this case it's a fiber optics IMU, which would give you angular rates and accelerations, and a Doppler velocity log, which is also a kind of a sonar that uses Doppler shift and frequencies to measure the velocity. However, this kind of sensor, you always need so-called bottom lock. So you need a ground below you to be able to measure the reflections of. So if they have kind of ranges different depending on the frequencies of the sonar itself. So typically between 30 to 100 meters. So if a higher frequency will give you, of course, more resolution, but then lower range. If it's a lower frequency DVL, then you will get longer range, so you can still estimate or get measurements of velocity if the ground is like, I don't know, 100 meters away from you. But of course, accuracy is a bit lower. The same kind of device, you can also operate it in another way, which is called acoustic Doppler current profiling, so or ADCP mode. And what you're trying to measure here is not the reflection, like not the strong reflection from a solid ground, but kind of the small reflections from like backscatter in the water. So if you're operating in any ocean or sea, all of the particulate matter that is spread around the vehicle that is floating in the water column will also reflect or cause acoustic reflections back. And this way, it's quite crude, so it's quite a noisy data that you will get back, but you can estimate from that the water relative velocity that we just talked about earlier. So if you have current, so if you have both in the same time, if you have ground bottom lock and acoustic Doppler current profiling, then you can estimate your water relative velocity. However, if you don't have bottom lock, then it gets harder unless you see, for example, markers or you have some other means. And the last part is the thrusters of the vehicle that we have. So if we have the thrusters, we can use, let's say, the inverse of the control allocation. So the thruster matrix to kind of calculate these tau and then pass that to the motion model. And then in this Kalman filter, we just propagate the states, which are in this case acceleration and velocities, plug them in the model, and then use this as a measurement model as well. So that's a bit in a nutshell. If you want to read a bit more about this, here is a paper by two of my colleagues, or now former colleagues. You can find it in the references. Exactly. So now taking this observer, UKF, plugging it in the system, and then using that for providing the feedback for a modulated controller, which is basically just the feedback linearization controller that I just talked about earlier. So this is kind of how the full system works, and again, the reference is always provided by the docking task that we have, basically. So whenever we observe from the camera the markers, we try to align by this glide slope and then try to go on a straight line until we dock. It's quite simple. Here's a bit like how the state machine works. So whenever we want to start docking, or whenever we see a marker, we go to a state which is searching for the station. If you detect a marker, then you go into the aligning phase. Now, once we are aligned in this green zone, and then we can see the marker as I said in front of us, then we go to this aligning by the glide slope. So we are like on the midpoint of this green path. And if we are on glide slope, then we are pushing also the robot forward. So we give then the goal to be the point in the docking station until basically it reaches. So this is like on docking is when it's whenever it's transversing this green point, and then whenever it docks. So you can either go to keep docking, and here you can see different things. So if it always loses the markers, it tries to. So here are some examples. I hope the video is not so jittery. I tried. So this is like one of the examples that we have. You can see here. Here it's like aligning by the station, and then it kind of there is a marker also inside, and there are a bunch of markers on the sides. However, here we have way more markers, because one of the things that we also have is that every time we enter this huge docking station, this DVL sensor, if you are in a very close range, we also don't get any feedback from the velocity control. So we have just more markers just to guarantee that we always at least detect one of the markers. Otherwise, we drift quite a bit. So, and the last thing is kind of the same as the first one. We just have the docking station on another robot. So here as well, you can see how close this DVL is to the ground. So there were lots of dropouts. So first, like without a model was really hard to achieve that docking. So especially like if you lose a bit the camera. So like also when you get too close to the marker, if you stop detecting the edges, then the feedback from these Aruku markers is also lost, and you start to drift. So yeah, some of the challenges that we faced doing that are, the biggest challenge is currents. We tried it once in the Northern Sea, and their currents are like quite strong, especially with the tidal currents, that when the tide comes and goes was quite hard to dock. Another very challenging thing is when we are in turbid waters, it's quite hard to detect the marker. I think later on Miguel will show you some footage also how it looks like when the water is not so clear. So you can only start detecting markers maybe when you are less than a meter close to them or something like this, which makes it also quite hard to. So this range that we have is gonna get way closer. So controller tuning is also something. So for one robot, once we fine-tune that, if the currents are not drastically changing, if we don't have strong currents, we don't have to change it. But of course, tuning it for different robots is a bit harder. The next stuff well, there are also challenges. I mean, we are attempting to do is to do docking with a rotatable thruster. So I'm going to show you later when I show you the tour this robot that we have, or this Lang robot. It has a rotatable thruster in the back, which is makes it non-holonomic or in the same time under-actuated. So you have to like control it by changing the angle of the back thruster. And for these, what I also mentioned earlier, like two methods that we're trying to test at the moment and compare to each other is LQR trees and reinforcement learning based docking. So hopefully in the next workshops in the project, I will be sharing a bit more results on these two topics. Yeah, so that's it so far for this part. So I think, first of all, maybe if there are any questions. Yes, Sasan?
So not related to what you were talking about, but in general, I just wanted to know if there is any possibility to share some of these models with us. I'm currently working on reachability analysis for hybrid systems, and you just showed this state machine, and obviously you have dynamic systems under each of these states. So that's a very interesting hybrid system model that we can use for doing some reachability analysis or providing some guarantees in general. So, and by the way, I'm looking for a case study to do some analysis for a real case. So is there any possibility to do that, or can I reach out to you later after?
Of course, yeah. Of course, you can reach out to me if you like afterwards, and we can talk a little bit more in details if you like.
Sure. How can I find your email address?
I'm gonna share it afterwards, but you can definitely, if you just look up my name, DFKI, it's
there. Okay.
It's there.
Okay.
It's basically just
Perfect.
my first name dot my last name at dfki.de.
Sure. All right. Thank you.
No worries. Any other questions? Carlos? Or Carlos, were you raising your hand from last time? Or?
Yeah, no, sorry, I was still muted. Again, Bilal, it's quite impressive to see all that you can explain basically yourself about the control of the systems now with the concrete case of docking. I'm curious. So you have this complex architecture, including an observer for docking, and there are, you mentioned these challenges, right? When there are not enough markers available, for example. Do you keep the same architecture, and do you just have the graded information in the signals that are used in there, or do you also switch some of the components of the observer, for example, on and off, or depending on the situation?
I mean, the thing is, this observer, the components are, let's say, the observer is always in a listen state, so it's always trying to listen to new updates from any of the sensors. And it is always doing this fusion. Every time it gets any update from any of the sensors, it will integrate it. So as long as they are all working, we were like, okay, why do we want to like remove some of them? So we know we have, let's say, the models, but at least the uncertainty of each sensor, which we integrate into our filter. And I mean, the issues that we face is basically, as I said, like cameras do not work on long range. So we have to rely on, we have this extra, let's say, redundancy a bit in the system. So cameras could drop out if we are far away. Velocity updates like from the DVL could also drop out if we are far away from the ground. And the USBL as well, if we are too close. So if we are too close, we don't see the marker, we don't have a ground, we also get dropout, and then we start to drift. So it's like, you know, every time you try to close a hole in your bucket, another hole would open up. So this is one of the challenges. I think also later on, Miguel is going to be talking about some other techniques that we're trying to experiment with, which is trying with a magnetic sensor to measure the distortions caused by kind of hard iron or soft iron that are present. For example, this docking station is just made out of steel, and if you have a magnetometer that whenever you get close to it, you can detect this distortion that this big metal thing does on the magnetic field of the Earth, basically. And by using some methods like neural networks, for example, you would try to learn Of course, there you need a fixed structure and in a certain location. So if you have ground truth, you could try to learn from the distortions the position. So you can add an extra modality to the system to try to. So yeah, I mean, as you're saying, like, I'm not sure. I hope I'm answering your question, but kind of guarantees. There are not really so much guarantees, right? So whenever you don't have feedback, you just have to live with what you have. And if you don't have any feedback of any of the sensors, the only thing that you try to rely on is either a good model, trying to adapt your model, for example, online if there are changes. And yeah, otherwise, I mean, nature is quite hard. You will drift.
Yeah. I was curious, so regarding this switching on and off inputs or components in your observer, is power also a concern there? Because I don't know if I can imagine that for the autonomy of these vehicles, power is important. It's true that if you are docking, you are about to get power, right?
Yeah.
But is that a concern to us to decide to switch off some sensors in some scenarios, basically?
Exactly. So, so basically. One of the things that we're trying to do, because also like of the scenario that we had with this space exploration, or if you try to do, for example, very long descents, you don't have to do, like, it's quite counterproductive to just propel yourself with a thruster all the way down. So there is a buoyancy, like a variable buoyancy engine inside of it, which is basically just like two kind of balloons or two bladders filled with oil. And then if you pump this oil inside of the vehicle, then you are heavier. So you could switch off, all of your motors, and maybe just keep your depth sensor to like go down a long descent, for example. And then once you're switching on your depth sensor or like an altimeter to like detect the ground. Whenever you detect the ground, then you can switch your system back on, for example, and do whatever maneuver that you want to have, and then go up in a similar fashion. So like switching, like making yourself more buoyant, switching off sensors, going up, and then once you get in the vicinity of the docking station and you can get, for example, USBL measurement or any acoustic positioning measurement, then you could try to find your way back to the docking station with minimal power and then switch on like the full sensor suit whenever you are in close range.
Thank you. Very interesting.
Okay. Any other questions? All right, then let's move directly to Christian, who's going to talk about the attitude control of the Cuttlefish robot.
Okay, thank you. Let me just share my screen. Okay, I hope you can see.
Not yet.
Okay, something's lagging. By the way, how are we doing time-wise?
Yeah, sorry. So maybe we can. So I think now your current talk is also like roughly 15 minutes or something like this, or how long?
Yeah, I assume so. Yeah.
And then we can have a break after that, and then do the last parts.
Okay. Okay, I'm just wondering why Teams froze. Okay. I assume you still can't see anything, right?
No, just a black screen. Maybe you can try to log out and log in again.
Okay, I'm trying.
Otherwise, we could also maybe. Sorry.
Okay.
Yeah, we can see it now.
Ah, interesting. Okay.
However,
Well,
yeah, now it's better.
let's just hope it keeps working. Okay. Yeah, I want to present you a different use case, a different robot that we are developing, which is the AUV Cuttlefish. And here we are deploying a cascaded control scheme, which I'm going to present in some, not too much mathematical detail, but to give you an overview and a feeling of what else is going on. Okay. Right. So first of all, I'm going to talk a bit about the AUV itself, so that you get a feeling, and then going to talk especially about two things: the control architecture and also the control allocation, which are have been developed here specifically for this AUV. And I'm also going to share like 2 short videos as a preliminary results. Okay, so Cuttlefish is our fully actuated intervention AUV. So that means it can be controlled in each degree of freedom. And one special thing about it is that it is not designed to be hydrodynamically stable, as you would usually have. Instead, it is designed so that the center of buoyancy and the center of gravity are close to each other, and that allows us to orient this vehicle in essentially any orientation that we like to have. It's equipped with 2 manipulators for intervention tasks. One of the manipulators is 6 degrees of freedom, so a full range of motion manipulator, and the other one is 4 degrees of freedom. The idea is mainly to have a shorter, sturdier arm for docking, but I'm going to talk about that more later. The whole vehicle is rather large, with a length of almost 3 meters, and the mass of about over a ton, essentially. It's actuated by 8 thrusters. You might be able to see it on the picture. So in each corner, there's a thruster pair, one horizontal and one vertical. And so we have, with these 8 thrusters, we have a bit of redundancy also in the movement. So even if one thruster decides to fail, then we are still able to work just fine. It's equipped with all the necessary sensors, so similar to what Bilal already explained. We have a DVL, Doppler velocity log. We have an IMU pressure sensor, a bunch of cameras and lights. And so these are not only for visual feedback to an operator, but also for marker tracking in the proximity of locations, of like offshore structures, say. And for global global positioning, we have USB-L also on board. If we say that the vehicle can be oriented in any way, so we really mean it. This is shows the vehicle not in a horizontal, but in its vertical position. And the idea here is that we are able to work with the manipulators on any structure, on any surface that we want. So be it on the ground, like on a pipeline, say, or be it on such a blowout prevention panel as it is shown here. The advantage of having this freedom of configuration is that we essentially extend our range of motion, our workspace. But we are also seeing like this. We have a lot of surface to put cameras, for example, or lights and sensors. So we can very well observe what we are manipulating, and can have sensors to watch from different angles, so that the manipulators are, by the way, like for example, not blocking the view of what we are trying to operate on. Yeah, so let me say just a few words about the project where this was developed. The Cuttlefish was developed in the project Mara IT, and the core idea of Mara IT was actually not to build this AUV. This was more of a necessity, but the core question was how can the flow of information be realized in a maritime applications, especially now like advancing to the digital age. A lot of things in the offshore industry are still done very hands-on in the sense that usually these intervention missions tasks are done remotely operated, and that means there's an ROV that is usually connected to with a large cable with an umbilical to a ship. And so there needs to be a ship and a crew, and your range of motion is of course limited, and so you need to always be with a large team and a vessel on site to do this operation. So it's very costly, very expensive, and that is of course also that is not only a problem for industry, but it's especially also a problem seeing that these structures are getting old. They need to be maintained regularly, and the higher the maintenance and inspection frequency, the less the chance of critical failure. And so in a way, it's very important for the environment, so not only economical, but especially ecological reasons to make these inspections cheaper, more optimized. And so that was essentially the idea. How can we do this? And here the idea with this Cuttlefish is that we have a submarine, like a resident vehicle, so a vehicle that stays in the water for long durations and can be deployed when needed. So, and one of the big problems is that intervention tasks underwater are very, very challenging, especially for autonomous systems. So there are very, very few examples in research that have shown this successfully. And everything in the industry is essentially done with remotely operated vehicles. And here we wanted to close a gap by providing a hybrid vehicle that can be autonomously flown to a target location, and there, when it has to work on a structure or stuff like this, it can dock with one manipulator, and through this dock, it can create a connection to an operator, and the operator can be based in an office. It doesn't have to be on a ship close by, and he can then operate this vehicle, do the task that needs to be done, do the inspection, get all the data directly into a business information system, and then send the vehicle back and maybe start controlling the next vehicle on the other side of the world. So that is sort of the idea behind it, and the reason why Cuttlefish came to be as a hybrid intervention AUV. So with a new vehicle, and especially the new problems that we were facing in the orientation control, we developed a new and dedicated control chain based on our previous experiences. And this is what I would like to go over now. So let's start with the first controller, which is actually maybe let's go a step back and then talk about the cascaded control. I mean, Bilal has been mentioning a little bit what this means. So essentially, a cascaded controller is the series of individual controller that can control various the system on various levels. So typically, what you always have is a low-level controller on the thruster, for example. So and then you have on top a different controller that just says, okay, please produce this specific thruster, but you don't really at this point care how this is done. So this is already in some sense a cascaded controller, and in case of this AUV, where we want to control the position and the orientation and the velocity of the AUV, we have the cascade essentially consists of a post controller and a nested velocity controller or twist controller. And then there are a few more components which I'm going into. So, but essentially the idea here is that you have a post controller, and the post controller calculates a reference for the twist controller, and the twist controller then calculates a reference for the AUV, or in this case, lower level controllers. Okay, so the controller itself then are really quite simple. So the position controller or the post controller consists of a position part and an attitude part. And on the position part, we have a single P controller for the 3 degrees of freedom. So that means the 3 degrees of freedom are controlled in a coupled manner, seeing that you can imagine if you have a pose error, or like a position error, then what the error essentially represents is a direction and a magnitude of this error. And so this direction directly translates to the 3 degrees and the 3 lateral degrees of freedom that we have. So all we need to control essentially is the magnitude of this error, to reduce the magnitude of the error. And that's what we do. The output of this post controller is then a reference velocity. So and one thing that's also done here is this output velocity, this reference velocity is subject to a saturation, which allows us to reduce overshoots. And essentially, what if you just suppose controller, if you just give a position reference, what it would mean is that that a high speed, when the error is large, a high speed is commanded, and the closer you get, the smaller the speeds get, and that means you can reach the if it's tuned correctly, you reach the position without overshoot. Okay, on the attitude controller it was a bit more challenging because here we have the problem of the gimbal lock to take care of, since we can orient the vehicle in any orientation we like, and that means that we cannot use a simple Euler angle approach where we just have one variable for each rotation. And gimbal lock, what this means is represented by this little graphics here, where if we turn a vehicle, in this case it's a plane, to a pitch angle of 90 degrees, typically it's a pitch angle, then we lose 1 degree of freedom. That's 1 degree of freedom, one direction of motion that we cannot longer achieve with Euler angles. So, but there are different ways. Bilal was also mentioning this. So quaternions is a method. Here we chose rotation matrices to represent our rotations, and the control law is stated here, where RD is the desired rotation, R is the current rotation, and based on these two, an error is calculated, and this error is fed through a P controller. So again, here we have a P controller, and it works in a similar way. So it's analogous to the position control, where we have like sort of a single controller for multiple degrees of freedom. So in a way, you can think a position error, a rotation error consists of an axis and an angle. So an axis of rotation that you need to do in order to minimize the error, and an angle to which you rotate around this axis. And so all we need to then control is the angle, to get the angle to 0. Okay, so next controller in the chain is the twist controller, and here we have a very simple PID controller, one for each degree of freedom. So here we don't have this coupled control anymore, but we have decoupled. Each degree of freedom has its own PID, its own characteristics, and the special thing about this controller here at this point is that it has two references. So it not only accepts a reference from the cascaded, so an internal reference from the cascade, but also an external reference that can be given directly. So, and the way it is implemented allows the user to decide if it wants to give either only a velocity command or only a position command or a combination of both. So, for example, just a velocity command might be very useful if you are remotely operating the vehicle. Then it is quite convenient to give, say, with a gamepad or a joystick to produce velocities that the vehicle needs to fulfill. And a combination of both, like a combined reference, is very useful for trajectory tracking. So if you have calculated a path and then a trajectory, what you have is position at each time steps. You have all the derivatives, and you can make use of these derivatives and increase the control performance that way. Then we have a few more nodes that are like blocked here together into like a model-based part. So we wanted to make use of models, although at this point we only have a very, very crude estimation of the AUV model. But the architecture is there to introduce this in as a feedback linearization, which Bilal explained in detail. But essentially, you are able to compensate nonlinearities on the hydrodynamics and also the hydrostatics. And then we have sort of special components here, which is compensating manipulator forces. So as we have two manipulators at this AUV, and when these manipulators move, then counteracting torque is induced on the vehicle itself. And this can be estimated to some degree. It is known and can be compensated in this component. Okay, last thing I want to talk about is optimal control allocation. So the procedure that we have developed for Cuttlefish, which sort of extends what I was talking about before, and just wanted to show you, like, okay, how are we actually applying this? And what are the specifics maybe of different systems that need to be taken into account? So the problem that we were facing in with Cuttlefish especially is that the thruster performance were very limited. Of course, you have the usual, like a maximum thrust and a minimum thrust, but the thrusters that we were using had were sensorless. So, and that means they have no hall sensor or anything to measure the position, and that is the position and velocity of the thrusters are measured based on the back EMF. If you know a little bit about electric motors, then this will seem familiar to you. But anyway, what it means is that at very low velocities, we have no feedback, and that means at very low velocities, the thruster cannot operate. Yeah, and that means in turn that whenever we operate the thruster, it has a non-zero idle thrust. So if it's active, if it's enabled, the thruster will run at a very low speed, but it's high enough to actually produce a thrust, and we need to take this into account. And then with the thrusters that we had a very interesting behavior for a thrust reversal. So because of it needs to, when the thrust is reversed, we need to essentially bridge the gap of this dead zone. So without really having any feedback, we need to first bring the motor to essentially to stand still and then reverse it. And this has to be done sort of in an open loop kind of way because we don't have any feedback. The behavior that we've seen with these thrusters and with the thruster controllers was that this was taking quite a long time on the one hand, and it was not even consistent. So what you can see here is that this open loop behavior, so this is in this area here. So what you can see here is that some of the thrusters show a very, very different behavior from some of the others. And so one thruster reached its steady state several seconds before the others. And that, of course, leads to huge problems. And that the range that we get is not at all what we desired. So the idea here was to develop a control law, or like a control allocation law, that prevents thruster reversal as much as possible. And not only that, but also to take into account the dead zone. And that is something that cannot be done with the method I've shown you before, or it needs to be extended a bit. And essentially the reason is that having a dead zone makes the problem non-convex. Yeah, here nochmal like just a short summary what we are trying to achieve. So given a desired range, tau d, we want to find thruster forces such that the difference between the resulting range and the desired range is minimized. We want to choose an F that respects the upper and lower bound, and even more importantly, an F that respects the dead zone, and that is quite critical. So if we have these, if you look at the graph down there, you can roughly see that the blue area is sort of the range of thrust that is allowed, while the set that is not blue is not. Yeah, and as I said, like thrust reversal should be penalized. And this was formulated into the following optimization problem. Here we so let's start looking at the cost function. So we see we have three terms here. The first term is should seem familiar. It just tries to minimize the thrust that is actually used so that we're not using overly much, as little as possible. Then we have a slack variable S, and we have a second slack variable SR. So if we look at the first slack variable, it should also seem familiar. This is just penalizing the deviation from the resulting range to the desired. So here tau is the desired range. And the second one is actually taking care of the thrust reversal. But let's first look at these two green equations here, and they are they take care of avoiding the dead zone. So, and how does this work? So we introduced this variable b, which is a decision variable, but it's a binary decision variable. So it can only take 0 and 1. And so what you see now is that if b is 1, for example, then what this means is that f must be larger than the upper dead zone. And in the second equation, it means that it must be lower than the upper bound. So if we go one step back, it means that it is lying in this kind of a blue set here. And then again, if b is, so that, sorry, yeah, that is when b is 1, and when b is 0, then what this equation means is that we need to be between the lower bound and the lower dead zone. And that, of course, is then refers to this set here. So we can decide whether we want to be in the one set or the other. And yeah, this is So B is a vector here, so this is individual for each of the thrusters. In a similar way, we take care of the thrust reversal. So what we're saying here is we have this F previous. This F previous is given by whatever thruster force we have been producing until this point. Or say the last. So the direction is currently running, and we say that this must also be essentially with these equations we check if it is in the lower or in the upper range, and depending on where it is, B and BR will be identical, which is good, which means we don't need to we have no thrust reversal, or they are different, and in that case we get thrust reversal and we allow this, but we have this variable, the slack variable as R, which will then be lead to a high cost. So essentially what it means is we allow thrust reversal if it's necessary, but we'll try to work without it. And in our case, since we are not only fully actuated, but actually over actuated, so we have some sort of redundancy, it means we can use some thrusters maybe a little bit more and others a little bit less instead of reversing some thrusters. So that is one thing that we implemented here, and this is no longer standard quadratic programming, but it is can be formulated as a mixed integer quadratic programming, and the mixed integer comes in with these variables that are with these binary decision variables. Just some preliminary results. So we haven't published anything yet, but I can still show you a little bit of the pitch and roll control that we have. So what you see here is the vehicle being in vertical position and then being commanded to assume the horizontal orientation. And while this is running, actually, there was no position control, so we have no position feedback. So the position is just is not controlled at all. It's just based on the velocities, or the linear velocities are tried to be minimized, and it still does quite a good job at changing the orientation. And in a similar way, we have the rotation in roll direction, where we can also assume various orientations. The thing is that the sensors, they are not really made for this. So the navigation gets a bit confused sometimes, say, when it loses track of the floor, for example, with the DVL. But yeah, that's something we're working on, as well as the position feedback to get like full state control very soon. And I think with this, I'm come to an end. Yeah. Thank you very much. And if you have some questions, please let me know.